Hello everyone, welcome back to my channel. So today we are going to discuss some questions related to classical mechanics. Okay, this session will be helpful for those who are preparing for SET examination, the upcoming West Bengal SET or the GATE examination, and also for GST examination. So the first question is, a beam slides on a wire in the shape of a cycloid described by the equation. Two equations are given, x equals to a theta minus sine theta and y equals to a 1 plus cos theta, where theta is ranging from 0 to 2 pi. First we need to find the Lagrangian function, and second is the equation of motion, and neglect friction between the bead and the wire. Okay, so first let us draw the diagram. They have said that a beam is sliding on a wire which is in the shape of a cycloid. So let us draw. This is our x coordinate, this is y coordinate, in the shape of a cycloid. Okay. Okay, so let us consider at any instant of time t, the particle is at a point Q. Okay, now the expression is given, x equals to a theta minus sine theta and y equals to a 1 plus cos theta. Okay, now first to find the Lagrangian function, we need to find the kinetic energy and the potential energy, right? Now kinetic energy is clearly we can say half m x dot square plus y dot square. Here our generalized coordinate are x and y. Now half m x dot and y dot. So we will separately first find out x dot, that is d t of x is given a theta minus sine theta. Okay. So a is a constant. So d dt of theta minus sine theta. What we will get is a theta dot minus sine theta, we will get cos theta theta dot. Okay. Similarly, we will find y dot d dt of a 1 plus cos theta. Okay. So we will get a is a constant. So d dt of 1 plus cos theta. 1 is a constant, so derivative of it is 0. So a cos theta will get minus of sine theta theta dot. Now we will substitute these values. We will get half m x dot square. So we will get a square theta dot minus cos theta theta dot square plus y dot square. So again a square minus of sine theta theta dot square. So we will get here half m a square theta dot square. We are taking a square outside plus cos square theta dot square minus 2 a dot theta dot cos theta plus a square sin square theta dot square. So clearly this and this we will get here. Sorry, a square is already I have taken it common. Here I have done some mistake. This is not a dot. This is theta dot cos theta dot square. Okay. So from here we will get sin square theta plus cos square theta 1, and this theta dot square and this theta dot square will add up to 2 theta dot square. Okay, and this 2 and here this 2, so this will cancel out. So we will get is m a square theta dot square minus theta dot square cos theta. I hope it is clear. So we are getting m a square theta dot square common 1 minus cos theta. Okay, so this is our expression for T, that is the kinetic energy. Now V, that is the potential energy. Next, potential energy. Now we are taking our x-axis as the reference level, this one. Okay, so this is our y. So now potential energy is mgy. So potential energy V, that is equals to mgy. Y's expression is given a 1 plus cos theta. So first thing, that is our Lagrangian function L, that is t minus of v. T we have calculated as m a square theta dot square 1 minus cos theta, minus of v is what, mga 1 plus cos theta. Okay, now second part is we need to find the equation of motion. So equation of motion is d dt of del L del theta dot minus del L del theta equals to 0. Here theta is our generalized coordinate. Okay, because x and y are related in terms of theta, are expressed in terms of theta. So theta is our generalized coordinate. So we are writing the equation of motion as del L del theta dot minus del L del theta equals to 0. Now del theta dot. So we are writing here 2ma square theta dot 1 minus cos theta minus del L del theta. So ma square theta dot square sin theta this cos theta minus cos theta, so minus sin theta, this is okay, minus mga sin theta, right, that is equals to 0. Now here we will get 2ma square theta double dot 1 minus cos theta. Again we will get 2ma square theta dot minus cos theta, we will get sin theta theta dot square minus ma square theta dot square sin theta minus mga sin theta, that is equals to 0. So this term we will get here 2ma square theta double dot 1 minus cos theta plus ma square theta dot square sin theta minus mga sin theta equals to 0. So from here, if we divide this whole thing with 2ma square, we will get theta double dot 1 minus cos theta plus half of theta dot square sin theta minus of g by a 2a sin theta, that is equals to 0. This is the main answer. Now you can just by seeing the options, since your questions will be MCQ types, you can adjust your answer in that way. Okay, you can do the further calculation. So this question was little bit easier. This type of question you can expect in SET examination. Okay, next question. Okay, so equation of motion, that means we need to find the Lagrangian equation of motion. So before that we need to find the Lagrangian. So we need to find the kinetic energy and the potential energy. So also before that we need to know the generalized coordinate, that is the minimum number of coordinates which are required to specify this motion of the system. Okay, so we will start from the basic. Here they have said a pendulum bob is suspended by a spring. Suppose this is the spring, okay, and this is the R naught is the original length of the spring, okay, and a pendulum bob is suspended by a spring and it is allowed to swing in a vertical plane. So this is something, this direction we call it as horizontal direction, and this is what we call it as a vertical direction. So now our final figure is what, this is our origin, okay, that is we are considering this is our reference. So from here a bob is allowed to swing with a spring, that is suspended by a spring. Okay, so this is our spring and this is the bob. Okay, this is the bob. Now this bob is allowed to swing, so it will swing in this way. Okay, so now since this is a spring, it has got a spring constant k. So the distance now this is r, because the spring will now stretched, it will be stretched, right? This is the original length r naught. Now when this is swinging in this way, so the spring will also get stretched. Okay, so it will be stretched by r minus r naught. Okay, it will be stretched by r minus r naught. R naught was the unstretched length and r is the total length. So it will be stretched by a distance r minus r naught. Okay, and this angle is theta. This angle is what? Theta. So here the variable coordinate is what? R and theta. See? Okay, r and theta are the variable coordinate. Like now you can say how theta is variable. Suppose at time t naught, this is the position of the bob, and at time t1, the position of the bob is suppose here. This is the spring attached. So this is theta 1. So theta is also varying and r is also varying. Okay. So our two coordinates which are variable coordinates are r and theta. And this is our diagram which we are going to use. Okay. Now you see, first we will find the kinetic energy. Now kinetic energy, we are representing it with T, that is equals to half of m r dot square plus r square theta dot square. Another term we get for phi, but here we need only two coordinates, okay, r and theta. So this is our kinetic energy. This is easy. Okay. Now potential energy. V. Now potential energy, one will be due to the spring and another will be, if we are taking this as the reference point, so this direction, if suppose I say this is y, so our potential energy will be minus mg y plus, due to spring we will get half k is the spring constant, and the stretched due to extension of the spring, this is our extension, this is our x. Basically we write now half k x square due to a spring which is stretched by a distance x. So this is our x here, so we are going to write half k r minus r naught square. Okay. Now here y is what? Here y is r cos theta. Cos theta is equals to what? Base by hypotenuse. So if you do in this way, you will get y equals to r cos theta. So we are getting minus mg r cos theta. What is half k r minus r naught square? So we got our we got our t. Now, so we got our Lagrangian L is equals to t plus v. So we are getting half m r dot square plus r square theta dot square minus of mg r cos theta plus of half k r minus r naught square. Sorry, this will be t minus v. So plus, and this is minus. Okay. Now equation of motion, d dt of del L del R dot minus del L del R equals to 0. This is our one set of equation of motion. Another is what? d dt of del L del theta dot minus del L del theta equals to 0. Now we will using equation 1 we will solve. First we will solve this equation. So what we are getting by using equation 1, d dt of del L del R dot, so we are getting d dt m r dot minus del L del R, so we are getting half m 2r theta dot square minus mg cos theta plus half 2k r minus r naught, that is equals to 0. Okay, so we are getting m r double dot minus m r theta dot square minus mg cos theta plus k r minus r naught equals to 0. Okay, so this is our equation of motion, first equation of motion. Now we will use this equation to find our second equation of motion. Now d dt of del L del theta dot minus del L del theta equals to 0. So what we are getting is d dt of del L del theta dot. Okay, now this is using our equation 1. Okay, see this, d dt of del L del theta dot. So here this is our dependence on theta dot. So we are getting here m r square theta dot minus mgr plus sine theta and minus del L del theta. Yes, only I am getting this two term. Okay, that is equals to 0. Now, see, with respect to time, r is also changing and theta is also changing. So here what we are going to get m r square theta double dot plus 2m r dot theta dot plus mgr sine theta equals to 0. So this is our second equation of motion. So this 2 is our answer. Okay, this is the first equation of motion, the second equation of motion. We are getting two equation of motion because they are two generalized coordinates. Okay, so I hope you understood this. Main thing is that you just need to find V and T. Okay, and then rest is calculation. Okay, next question. Okay, so next question is what? Using Poisson bracket so that the transformation Q equals to and expression for P equals to is given is canonical. Now since in the question they have said using Poisson bracket, so the essential condition by using Poisson bracket that the transformation is canonical or not, we know what we need to find is Q comma P equals to 1. Okay. So now expanding this Poisson bracket, what we will get is del Q del P by minus, okay. Now what we need to do is just we need to do the partial derivatives. Also furthermore we can also show that the canonical transformation of Q comma Q is 0 and P comma P is also 0. Okay, so now we will proceed with this. The expression is given. So first let us find the term individually. So we are getting del small q. Capital Q is given e to the power minus 2 q minus p square whole to the power half. Okay, so this we are going to get e to the power minus 2q minus p square whole to the power half, and here we are going to get minus e to the minus 2q. Okay, next del p by del small p, we are going to get del p. Expression of p is cos inverse PEQ. See, this you can also solve in this way. This is one process. Another process I am telling you. See this, P is given cos inverse PEQ. So this can be written as cos P PEQ. Correct? Now, if you differentiate this, you will get minus of sine P del P and EQ del of P. So now del P by del P small p e to the power q minus sin P. Now sin P can be written as 1 minus cos square P. Correct? So the expression which we are getting is cos P is this. So we are getting P square e to the power 2q. Okay. So whichever is you are comfortable in, you can do. Okay, again we can solve this. If we divide by e to the power q, what we are going to get is minus e to the power minus q minus 2q minus p square. Okay, we got the two expression. Now del q del p. Okay, now del q del P. So del P of Q is given e to the minus 2Q minus P square whole to the power half. Okay. So del P. So we will get here minus P by e to the minus 2Q minus P square whole to the power half. Now next is del P by del small of P. So this one again we can use this here. So from here we can say del P, del small p we need. This we have already calculated. Okay, so we need to calculate this one. Del P, del of Q. So from here we can write, uh, we know P equals to cos inverse P e to the power Q. So cos of P equals to P e to the power Q. So we will get minus sine of P, that is equals to P e to the power Q del of Q del of P. So we will get del P del Q P e to the power Q by root minus 1 minus P square e to the power 2Q. Okay, again we can divide with e to the power Q. We will get e to the power minus 2Q minus of P square. Okay, now substituting all these values, here we are getting minus e to the power minus 2Q by e to the power minus 2Q minus P square whole to the power half, and here minus 1 by e to the power minus 2Q minus P square whole to the power half minus del Q del P, that is minus, and here there is a minus sign, minus P e to the power minus 2Q minus P square whole to the power half, and last term del P del Q which we got here, that is again a minus sign, minus P e to the power minus 2Q minus P square whole to the power half. Okay. Okay. So what we are getting is e to the power minus 2Q by e to the power minus 2Q minus P square whole to the power half minus this minus. So this one will cancel out. We will get minus P square by e to the power minus 2Q minus P square. No, half will be not there because this half and this half we will multiply, so we will get e to the minus 2Q minus P square. So in the numerator and denominator we are getting the same term, so that is equals to 1, hence proved. Okay, just you have to do the calculation part. Okay, I think this process is little easier, this way of doing. Next it's up to you. Okay, next question. Okay, so question number 5, it says that the mutual potential energy V of two particles depends on their mutual distance r as follows. V equals to A by R square minus B by R, where A and B both are greater than 0 and they are constants which does not depend on R. For what separation R are the particles in static equilibrium? So, as in the question, they have given us the expression potential energy which is dependent on the mutual distance r as A by R square minus B by R. That is, one part is the repulsive part and the second part is the attractive part. Now they are asking for what separation r are the particles in static equilibrium. So for being the particles in static equilibrium, what we need to do is we will differentiate the potential energy with respect to r, and that must be equals to 0, and then we will get the separation r for which the particles are in static equilibrium. So what we are getting is ddr of A by R square minus B by R, that must be equals to 0. So after differentiating, what we are getting, minus 2A by R cube plus B by R square equals to 0. So 2A by R cube, that is equals to B by R square. So we are getting R equals to 2A by B. So this is the mutual separation for which the particles are in static equilibrium. Okay. So this was an easy question. This type of question you can expect in GATE, SAT examination and MSc entrance examination. Okay.